right, thank you. My presentation is on a version of the double punch test that was developed for quality control of UHPC. So I just want to start with a really big disclaimer that we only would like to use this for quality control. There are a lot of great tension tests that are out there that give great stress versus strain information and that we think are great for initial mix qualification. And what we imagine this test would be better for is for the quality control. So you make a mix in the field and you want to make sure that the results are what you expected with your original mix that was already qualified. So, the little spiel, but this purpose is reiterating that we want this to be for tensile strength of UHPC, because obviously that's an important parameter that normal concrete doesn't have the same properties of. And we want to improve upon the split cylinder test. That's sort of the test that we saw as the normal concrete quality control tension test. But some problems with it is it doesn't give a measure of strength after cracking. It just gives you one value. And then it also tends to inflate those results because in the split cylinder test, the region that is cracking is in compression. And with the fibers, it adds friction to the fibers. They're being held more tightly in the concrete, so you get higher stresses than what's really there. But what we like about the split cylinder test is that it's a low-cost test and pretty much all labs have the equipment to perform it. So we wanted to keep that when we were looking at a UHPC test. So what we looked at was the double punch test. This is a test that has been used in some other countries. We looked at the Spanish specification. Sometimes this test is called the Barcelona test because it is used in Spain. And you have two punches, so double punch, one on top and bottom. These are small steel cylinders that are compressed into the concrete, and you get these what are called failure cones. So the concrete breaks in a cone shape typically, and then as you continue to compress, those concrete cones push out the rest of the concrete, and the resulting cracks look like this. So you get this tensile failure in the outer region of the concrete. The vertical cracks form due to the concrete cones pushing everything outward. And you can see the setup of that test on the right. So when we were looking at this test method, we wanted to modify it, like I said, to be like the split cylinder test where any lab can perform it. And so the two main modifications we wanted to make is to be able to run it in a standard compression machine. And then second, to use a low-cost data collection method. So we wanted to look at how, when we made those modifications, what parameters we needed to control in our test method. And then finally, if our modified double punch method correlates well to other methods like the direct tension test that FHWA has done and ASTM C1609. It's a flexure test. Our first modification is to use a compression machine in our test method. The original test uses a displacement control rate, but most labs, especially maybe like a regional DOT lab or labs that might be needing to do this quality control test, they don't have a machine that has a displacement rate control or a closed loop displacement rate control. So we wanted to see if the load rate that our compression machine was giving out correlated to a displacement rate. And you can see the graph. We are getting pretty good correlation at lower load rates. Once we got faster, we got not as good correlation, but I put those orange lines in there because 0.5 millimeters per minute is the value that the Spanish specification uses. So that is giving us something in our linear region, and it correlated to a little bit lower than 400 pounds per second in our compression machine. The second modification was using equipment to measure our displacement that would be available to most labs. So the original method used what's called a chain extensometer. You can see it around the center of the specimen on the right picture. And that was a very expensive piece of equipment that we didn't think a lot of labs would be willing to purchase. So we moved to vertical displacement. We found in the literature that a lot of other researchers had already done this. They had compared what we would call circumferential displacement or expansion to vertical displacement, and they found a good relationship. So there are other people who had said vertical measurement is fine. We used 4 string potentiometers, and we found that we weren't getting very different results between the 4. So we switched to 1, and that is a dial gauge, because we noticed with the string potentiometers, you still needed a data acquisition system that was going to have a computer involved, and you'd have to probably write a code to convert your string potentiometer value to displacement. So for a lot of these labs, that was kind of a difficult step, and we wanted to just use a dial gauge, which is very inexpensive to buy, really easy to implement, obviously. But what you're losing with that is this continuous data. So the string potentiometer is connected to the computer, and also our machine we had to wire up to a computer as well. That gave us a nice curve of stress versus displacement. But when we used the dial gauge, it wasn't continually recording for us. You had to have a person writing down what the dial gauge said and writing down what the machine said at the same time. So you got discrete points, and that gave us a result that didn't totally capture the whole curve, but it got the general trend. And we wanted to see how far off are these two readings between the continuous data from string potentiometers and our dial gauge discrete points. So we measured the toughness of these two, which is just calculating the area under the curve. And we did this with multiple different displacement intervals. So the one shown there shows every 0.025 inches. We also did one every 0.05 inches and then every 0.01 inches to see how frequently we needed to take this data. And here's the comparison between the continuous data and then those incremental ones from the dial gauge. We found that at 0.2025 inches, which I showed previously, on average, we got a difference of 0.55%, which is pretty good. The worst case scenario out of 22 specimens was that we were off by 1.5% in our toughness calculations. And we thought that's pretty good for a quality control test just to be off by that much. So we moved ahead with using this dial gauge instead of our more complicated data collection methods. When we looked at the parameters, I already talked about toughness. Here's an example of what our results typically looked like. We also looked at our maximum stress, and then we looked at a post-cracking stress, because some of the concretes that maybe were not as well reinforced, they might get a good maximum stress and then immediately drop in their strength. So we wanted to specify a displacement that would be well enough post-cracking so we could measure how the specimens did after that highest value. So next we looked at a ruggedness study of our test method, and a ruggedness study looks at a procedure and sees how small changes to the procedure will affect the results. So here are the 4 different changes that we made. We looked at different casting methods of our specimens, surface roughness, which is just whether or not we ground the tops of them with a cylinder grinder, load rates, and remember, like I said, 400 or a little bit under 400 was about what correlated to the displacement rate specified. And then punch centering on the top. What we found when we did statistical analysis was that the only one of these that mattered was the casting method. And not only did it matter, but it mattered quite a bit. So I have 99% confidence interval, but I look back, it's actually 99.9% confidence interval that casting method made a difference. We were finding that the specimens filled with the scoop were having a lot higher tensile strength than the ones filled with the bucket. And I put slow and fast filling method because as we were in the lab, filling the specimens with the scoop did take a lot longer. And what we thought is that this self-consolidating concrete is flowing to fill the mold. And as your concrete flows horizontally, the fibers within your concrete are also flowing horizontally. And we're probably getting this preferential alignment of fibers in the horizontal direction. So when you have cracks that are forming vertically, your fibers that are horizontal are more likely to intersect those cracks and you're going to get better performance. And we tested this by doing CT scans, which are 3-dimensional X-ray images of some of our concrete samples. The one filled with a scoop is on the left and the bucket's on the right. We color-coded the fibers. These scans are only showing the fibers. We color-coded the fibers by orientation. So in these pictures, anything red is a horizontal fiber and anything blue is a vertical fiber, and green is somewhere in between. You can see a clear difference in the colors. There's a lot more red fiber in the scoop filled specimen, which is what we predicted. So then we wanted to look at how this correlated to the FHWA's direct tension test. This is a gold standard of tension tests for UHPC. We wanted to make sure we were getting good correlation. So we looked at toughness and post-cracking strength of both specimens. That showed good correlation in both cases. And then we did a round robin study. So we took 8 labs across the state of Florida, and we gave them 3 samples of a 1.5 fiber content and 3 samples of 2.5 fiber content, and they tested them for us. Here is the spread of the data. So there are 24 samples shown here for 1.5 and 24 for 2.5. And then here's the lab averages. So each lab did 3. We took those, found an average, and plotted those as well. You get a lot less overlap, especially in the peak stress data when you look at lab averages. And if we use this specification in Florida, we would have a lab do 3 tests at least and then average those out for reporting. Here are the coefficients of variation of the test. They're arranged. So the left number is showing coefficient variation for all 24, and then each lab average is compared for the coefficient of variation on the right. So you can see those values are lower, the average ones. And for comparison, the ASTM C1609 reported COV of 9.2% for peak strength, and that bottom value is their toughness type parameter, and that's showing a 17.3% coefficient of variation. So we're in that range, but just note that ASTM C69 is single operator, and ours were different operators with different machines as well. And in addition, the C1609 ones aren't UHPC, they're probably just fiber reinforced concretes that were used for that. So not a perfect comparison, but we're in the ballpark there. So in summary, how this relates to overall tension testing of UHPC is that we really want to have that measure of toughness and ductility. And this test method does provide that, which makes it really a step up from the split cylinder test. And the modified double punch test, as we showed, is easy to perform. We trained our undergrads to do it in the lab. So not that we have inexperienced undergraduate students, but they were able to perform it. Everyone that we had at the round robin study was after about 1 or 2 practice specimens, really got the hang of it. And it doesn't require a lot of money or equipment upgrades to perform, which was really important to us for Florida, because we want all of the regional DOT labs to be able to do this when they have UHPC projects in their area. We saw good differentiation between the mixes, and we got good correlation with the FHWA direct tension test. And then I showed the coefficients of variation. They related pretty well to what we see in ASTM C1609, which is also a very good test, but it does require a displacement rate, and not everyone has a machine that can do that. It also requires LVDTs, which requires a data acquisition system. So in comparison to C1609, this test requires less special equipment to perform. So the recommendation that we gave to the Florida Department of Transportation was we could use this mix for quality control, but we still want to qualify mixes with either direct tension test or ASTM C1609. And with that, I want to thank the Florida Department of Transportation and the companies that donated materials to us, everyone who helped me mix, and then the participating labs, which I didn't list, but we had the Florida Department of Transportation Materials Lab and Structures Lab, as well as regional labs 1, 2, and 3, and then FIU, University of Miami, Florida State, and Durastress as well participated. Thanks.
We certainly have time for a couple of questions from the audience and then online. Any question? Yes, Dr. Kaya?
Thank you for a very interesting presentation. I was intrigued by the fiber distribution when you do it slowly with the scoop versus you cast it. So what is the recommendation for the casting of those samples, and how many samples do you have to test in the lab to get good reliability? A coefficient of variation of 18% is a bit alarming. So if you were to do it within the same lab with trained students, would you get like much lower numbers?
We did do kind of an internal study we used 3 different machines, but the same operator, and we didn't find any statistical difference in the values from each of those. We would recommend that Florida use just a bucket method, or if you're writing it in spec form, they should maybe use more of a time limit. Like specimens must be filled in under 10 seconds or something, so that you make sure your concrete doesn't have time to level off. I do think there's, maybe the potential that if you want to recommend that they're filled with a scoop, then you need to apply some sort of safety factor to that, because they were giving us consistently higher values when you filled with a scoop. I think in the field, if you're making the specimens, these are 6-inch by 6-inch cylinders. Time-wise, nobody's going to want to use a scoop to fill them anyway, because it did take a while. So I think we would recommend, they need to be filled in under a certain amount of time.
Thank you. There were a question, one in the back and then go to the front.
Professor, I'm wondering if you consider the rheology of the UHPC when you, for example, the fast casting use a bucket and the slow casting use a scoop. Maybe I assume that if the plastic viscosity of UHPC is high enough, maybe the dispersion will close. And if the viscosity is lower, maybe the difference should be huge or something like that.
Yeah, that is a good point. And we unfortunately just used one mix design for these. So I think that could make a difference in how the concrete fibers orient themselves.
Dr. Haber?
So I might have missed this, but I guess my question is, right, so like you have a material criteria that like the contractor needs to provide certain performance characteristics in your material. This is a quality control test. You need to calibrate this test according to like the desired mixture, or like, is there a magic number for all UHPCs? Like, what's the metric that you're measuring this against is, I think, my biggest question.
Sure. So we did give the Florida Department of Transportation some values for this that we would want concretes based on their tensile strength classes, because they have different tensile, or their goal is to have different tensile strength classes for concrete. We did do a comparison between the direct tension test and this test on peak strength, and the equation in the Spanish specification did a really good job of mimicking the peak strength values. So we felt like that was a good equation to take our load and translate it into a stress value, because those were correlating really well. We got a lot of variability in our peak stress value of the direct tension, which is why I didn't show it, because we used a range of fiber content. So some of ours had like 1.5% fibers, and we got a lot of variability in peak stress there. But the correlation was good with DoublePunch test of 1-to-1. We would want to focus on the toughness value too. So you need to meet a peak strength value and you need to meet a toughness value. That would be the goal, and it would need to be calibrated. I mean, if you're getting a mix approved initially and you're going through the direct tension testing process, to do 3 of these specimens is so easy compared to how much work that is, that I can imagine them just doing both so that you have a good correlation to what your mix is.
Well, with this, thank you very much.